All right, welcome back. We're still looking at the unraveled exact couple coming from a filtration of a space. So I've got this filtration, and we've said loosely that we get a spectral sequence, or I suppose I've claimed that we get a spectral sequence where the E1 page starts with the homology, the relative homology of the filtered pieces. And we haven't talked about the convergence at all, but I claim that this cooks up the homology of our space. Well, really it'll be an associated graded for some filtration of that module. But we'll get to that later. For now, I just kind of want to put some of this into some context. And I was drawing this unraveled exact couple, but I wasn't drawing any of the spectral sequence. So let's look at this E1 page and see what we have here. And on the E1 page, well, what are we supposed to do for the 0, 0 spot? I guess we're supposed to take h0 of x0, comma x minus 1, so that's just the empty set. And then if we go up 1, we increase q. That's going to increase our homology degree and not change our filtration. So, okay, that'll continue. Everything in this column will look like the homology, the relative homology for the same filtration spot. Let me just say that continues. And then for p equals 1, well, now we should be looking at homology of, I'm going to need more space, homology of x1 comma x0. And I should have p plus q homology there, so that's 1. And then I have h2 of that. If I move up, I'm only increasing q, which doesn't change the inside. And now I'm thinking about spaces, and so, well, actually, depending on what this filtration is, this could exist. So, of course, there could be negative homology, but again, I'm thinking about spaces. But I'm sort of thinking about that CW filtration, and then I know that H0 of x1 comma x0 would be 0, but in general, for some filtration, that's not necessarily the case. Maybe x1 included some 0 cells. Let me extend this picture a little bit further and look at the next column. So I'm going to increase p by 1, so now I should be looking at homology of x2 comma x1, and I see that this is actually h2, and so below it is h1, and below that is h0. So this is not necessarily a first quadrant spectral sequence. Then above it I've got h3, h4, so on. I think you get the idea. And of course continues in this direction as well. Okay, so I just think it's helpful to kind of have it all laid out there. And what we should ultimately be learning about is some associated graded of the homology of X. We'll have to come back to that. But I first wanted to give you an example, sort of a sanity check here. So suppose this was actually the filtration I was trying to think of in the first place. So a cellular filtration for our CW complex. So that xn is our end skeleton. Well, then what happens? For hn of one of these relative things, by excision, we actually get the reduced homology of the filtration quotient. And that's, of course, going to be a bunch of copies of the integers. It's going to be some free module generated by the cells that we have, a degree p. So this is if n is equal to p. And of course, for each of those things, I guess I should say, this is a wedge of a bunch of spheres. And so I'm getting a bunch of copies of z if n is equal to p, and 0 if not. These are a bunch of p spheres. Okay, and so when I take the same picture, maybe I can even squeeze it in here, and I write this down, well, of course, here I've got the reduced homology of x0 with a disjoint base point, because I'm doing this relative the empty set. I really just mean h0 of x0. Then I should have h1 reduced of x1 mod x0, so a wedge of circles. And then I've got I'm writing too low down, so this thing keeps shifting, sorry. Then I have h2 of x2 mod x1, and so on. But of course, when the degree of the homology doesn't match the filtration degree, I'm going to get 0. So I have 0 everywhere up here and everywhere below here. So I really just had this one line. Now, I said this was an E1 page and I only drew the groups, but I didn't write anything about the differential. On the E1 page, our differentials go to the left. These are D1s. And so on this, in this particular example, we just have these differentials to the left. Of course, this continues. And you can check from the definition of this differential that, in fact, this is exactly the same differential you see in the cellular chain complex. And so this is the cellular chain complex that we've written down here. For our space. Okay, so really, a spectral sequence is just a fancy version of our cellular chain complex, and it's just a souped up version of that. And in fact, to some degree, to build this thing, all we did was write down a bunch of long exact sequences. So it is entirely a bookkeeping device for all of that data, putting it all into this one picture here, and then hopefully allowing us to compute more easily. But nothing that's there didn't show up in those long exact sequences. Somehow all of that data was there, but in that unraveled mess, and the hope is that if we sort of put it in this nice little package, then it'll be easier to work with. Of course, I won't be able to convince you of that until we see some examples and actually do some computations, but this is exactly what we're after. Okay, so let me stop there.